Hi, and welcome to the video for section 4.3 for Math 126. This is the only video for this section. In section 4.3, we're going to look at the log function. So by definition, we have let A be a positive number with A is not equal to 1, then the log function with base A and we denote this in the following manner. So this is denoted log with a little a next to it. So instead of having it as an exponent, it's sort of a subscript. So denoted log of A is defined by the log base A, we call it, of x is equal to y. So if I have this notation, I'm going to classify this as the holy grail of our log functions. If we're working log problems and you get to a point like this, and if you're stuck, so you're like, man, I'm stuck, I'm not sure what I'm supposed to do on this, think back to this property, which is, if we have something written like this, this means the same thing as if we take the a, move it to the other side, so a to the y power, this is equal to our value of x that was after the base. So again, the base was of log. If you make that the exponent here, that's equal to the value that was in front of this log. So this is basically in sections 1 and 2 of chapter 4. We looked at exponential functions and specific types of exponential functions. Log is also another type of exponential function. It's actually even the reverse, sort of reversing the process. So let's look at a couple examples. If I have log, whoops, not 10. If I have log base 10 of 100,000, if I want to know what is this equal to, well, this is equal to 5, because by our log definition, so this is because 10 to the 5th power is equal to 100,000. So if I didn't get 5 as an answer and I had to simplify this, I'm asking myself 10 to what power is equal to 100,000? 10 to the 5th power. So similarly, if I have log base 2, and that's what we always call this, so this is our base, and the y is our exponent. So if I have log base 2 of 8, this means what? 2 to what power is equal to 8? Well, 2 to the 3rd power is 8. So therefore, log base 2 of 8 is equal to 3 because 2 to the 3rd power is equal to 8. So lastly, maybe try this one. Log base 2 of 32 is equal to what? So this means 2 to what power is 32? Well, 2 to the 5th power is 32. So because 2 to the 5th is 32, this piece simplifies to 5. So as I said, this is sort of our holy grail. If you are doing a log problem, you're going to have log problems on your in-class exams, you'll have log problems on the final. If you get simplified to a point like this, don't stop. Ask yourself, can this be simplified further? And can it be simplified further? Because I want to know the base to what exponent gives me this value. So let's look at some properties of logs. So of the log function, we have the various properties. First, log base A of 1. So that means what? A to what power gives me 1? Well, anything to the 0 power gives you 1. So log base A of 1 is equal to 0. Log base A of A, so A to what power gives me A back? Well, that's 1. So if these numbers are the same, if I have log base 3 of 3, that's 1. Log base 8 of 8, that's 1. The next property we have, log base A of A to the x power simplifies to x, which makes sense, right? If I was to move this around and say A to what power gives me A to the x, well, that would have to be the value of x itself. So if I had log base 4 of 4 to the 3rd power, it would be 3. Whatever power that's raised to, that's the value that I get when it's simplified. And lastly, if I have A to the log base A of x power, this is also equal to x. So we have these 4 properties. We also have the graph of the log function. And this isn't specifically in the book, I don't believe, but if you're going on to Math 181, just as in the earlier sections with the exponential function, I pointed that out to you guys, it's super important to know what the log graph looks like. You're going to be doing a lot of work with the log function, and so you need to know what does it look like on the graph, what's its domain, what's its range. So let's take a look at that. So let's just call it log graph. So the log function graph. So if f of x is equal to the log, you can call it base 2 of x. And the base doesn't really matter here because the base is just our exponential, but the graphs are all going to look the same. It'll change a little bit because of the base, but it still has the same general shape. Well, let's build a table here. So if we call this thing y, so let's go sort of backwards here because that's the way the log function works. If y is equal to, let's say, positive 3, well, what's my value? This whole thing means 2 to the y power is equal to x. So I know we normally pick x values for our table, and then we figure out the y. We're going to go backwards here. So if y is 3, then x is 2 to the 3rd power, which is 8. How about if y is 2? That would be 2 squared, which is 4. If y is 1, 2 to the 1st power, which is 2. 0. So if y is 0, 2 to the 0 power is just equal to 1. Anything to the 0 power is 1. How about negatives? So if y is negative 1, if y is negative 1, this becomes 2 to the minus 1 power, which with our exponent rules is what? 1 over 2 to the 1st power, which is just 1/2. So can we see a pattern developing in the table here? As these numbers keep going down by 1, 3, 2, 1, 0, negative 1, negative 2, negative 3, what's happening to these values? 8 divided by 2 is 4, divided by 2 is 1, divided by 2 is 4, divided by 2 is 2, divided by 2 is 1, 1/2. If I divide it by 2 again, I get a 4th. If I divide it by 2 again, I get an 1/8. If you see that pattern. So if I was to draw this out, So if I graph this, what do I have? 8, 3. So 8, 3, 4, 2, 2, 1, 1, 0. So does that make sense? Log any base of 1 is going to be 0, and that's what we have here. So log of any base of x, which is 1, has to be 0, our y value. So it holds true with this property. And then x is 1/2, y is -1, 1/4, -2, 1/8, -3. So what we end up getting for a log function graph is something that looks like that. If it's the base log function, it's always going to go through the point 1, 0. It's always going to be in the positive domain. I can't pick any value for y that's going to give me a negative x value, right? So if my base is positive, which it has to be for the log function, I can't take any positive number to any exponent and get a negative number out of it. So this is what your log graph looks like. And I'm telling you, try to commit this to memory, put it on your cheat sheet. When 181 comes, go back to that cheat sheet and refer to it, because this is what it looks like. How about our domain? Well, the domain is going to be all the positive numbers. So 0, which we don't include 0, it never gets there, so it gets a parenthesis. So 0 to infinity, and the range of this function is -infinity up to +infinity. So that's what our domain and range look like, and what the graph of the log function looks like. So that case there, that example, we had a base of 2. We also have what's known as the common log, and that says the following. The log function with base 10 is called the common log. And is denoted by omitting the base. So we've talked about the invisible 1. If I have x plus 3, there's that invisible 1. If I have the square root, there's the invisible 2. Now if I have log base 10, there's the invisible 10. So instead of writing log base 10 of x, I simply write log of x. And that means the base is invisible, it's 10. We just don't write it. We also have what's known as the natural log. So that was common log. Natural log the natural log, if you are taking 181 at some point in the future, this is what you're going to see the most. Natural log is the most commonly used in calculus. And this says the following. The log with base e, which you remember from the earlier videos, section 2 I believe. So the log with base e is called the natural log. And is denoted by so we write ln. I know it looks like 1, but it's really an L. ln of x, which just means the log base e of x. Let me get that out of there. So it's a small letter L, ln of x, natural log. Why they write it backwards, I'm not sure. Maybe they didn't want to write NLX, so they write ln, natural log. And so that means what? So it means if we have natural log of x is equal to y, so off of our same principles of the base log, the holy grail log function, this means what? This means e to the y power is equal to x. Because we don't write an e down here, but if there was an e, it would come out to the side. Our exponent is y. So natural log of x equals y means that e to the y power is equal to x. So finally, to wrap up the video here on 4.3, we have properties of natural logs. And they follow very closely to those of the the properties of log with base A. We just have the different base. But essentially we're saying that the natural log of 1, so again, if we think there was an e here, e to what power gives me 1? Well, again, it's 0. If I have the natural log of e, these guys are essentially dueling functions, natural log and exponential. So if I have the natural log of e, and this is the one, trust me, if you get to calculus class, you got to remember this. Natural log of e is just equal to 1. So they sort of are canceling out functions of each other, gives us our value of 1. If I have the natural log of e to the x, so again, these functions essentially cancel each other out, so this just gives me x, whatever that exponential is. And I can switch them if I have e to the natural log of x power. Again, they're sort of canceling functions, so this gives me x. So as I reiterated, if you are going into a calculus class at some point in the future, this is probably going to be the most important, aside from the graph of the log function, the idea of the natural logs. That's what's going to be used so much in that calculus class. So that wraps up video 1. Again, that's the only video for section 4.3. Come on back and we're going to look at the video for section 4.4.